Good day everyone, I am Liz Pesco and I am here to report about the preparation of data and presentation of rainfall data under Chapter 2 Precipitation. So first is the preparation of data. Before using the rainfall records of a station, it is necessary to first check the data for continuity and consistency. The continuity of a record may be broken with missing data due to many reasons. In case of a missing data, it can be estimated using the data of the neighboring stations. In these calculations, the normal rainfall is used as a standard of comparison. The normal rainfall is the average value of rainfall at a particular date, month, or year over a specified 30-year period. The 30-year normals are recomputed every decade. Thus, the term normal annual precipitation at Station A means the average annual precipitation at A based on a specified 30 years of record. For the estimation of missing data, if the normal annual precipitations at various stations are within about 10% of the normal annual precipitation at Station X, then a simple arithmetic average procedure is followed to estimate Px by using the first formula shown in the video. And if the normal precipitations vary considerably, then Px is estimated by weighing the precipitation at the various stations by the ratios of normal annual precipitations. This method is known as the normal ratio method, and in this case, we use the second formula as shown in the video. For better understanding, we have an example. The normal annual rainfall at stations A, B, C, and D in a basin are 80.97, 67.59, 76.28, and 92.01 cm respectively. In the year 1975, the station D was inoperative and the stations A, B, and C recorded annual precipitations of 91.11, 72.23, and 79.89 cm respectively. Estimate the rainfall at Station D in that year. So as the normal rainfall values vary more than 10%, the normal ratio method is adopted, which is the second equation that was previously discussed. So we have PD is equal to 92.01 divided by 3 times the quantity of 91.11 over 80.79 plus 72.23 over 67.59 plus 79.89 over 76.28. So we have an answer of 99.48 cm. Next is the test for consistency of record. If the conditions relevant to the recording of a rain gauge station have undergone a significant change during the period of record, inconsistency would arise in the rainfall data of that station. Some of the common causes for inconsistency of record are shifting of a rain gauge station to a new location. Second is the neighborhood of the station undergoing a marked change. Third is the change in the ecosystem due to calamities such as forest fires, landslides, and fourth is the occurrence of observational error from a certain date. The double mass technique is used for checking the inconsistency of a record. This technique is based on the principle that when each recorded data comes from the same parent population, they are consistent. So when you make a graph, values of summation Px or the accumulated precipitation of the station X are plotted against summation of Pav for various consecutive time periods. Summation of Pav is the accumulated values of the average of the group of base stations. A decided break in the slope of the resulting plot indicates a change in the precipitation regime of Station X. The precipitation values of Station X beyond the period of change of regime is corrected by using the relation P sub Ex is equal to Px times Mc over Ma, where P sub Ex is the corrected precipitation at any time period t1 at Station X. Px is the original recorded precipitation at time period t1 at Station X. Mc is the corrected slope of the double mass curve, and MA is the original slope of the double mass curve. The graph shown is an example of a double mass curve. A change in the slope is normally taken as significant only when it persists more than 5 years. The double mass curve is also helpful in checking systematic arithmetical errors in transferring rainfall data from one record to another. Next is the presentation of rainfall data. A few commonly used methods of presentation of rainfall data which have been found to be useful in interpretation and analysis of such data are given as follows. First is the mass curve of rainfall, second is the hyetograph, third is the point rainfall. So one of the most commonly used methods is the mass curve of rainfall. The mass curve of rainfall is a plot of the accumulated precipitation against time plotted in chronological order. Records of flow type and weighing bucket type gauges are of this form. Mass curves of a rainfall are very useful in extracting the information on the duration and magnitude of a storm. Also, intensities at various time intervals in a storm can be obtained by the slope of the curve. For non-recording rain gauges, mass curves are prepared from a knowledge of the approximate beginning and end of a storm and by using the mass curves of adjacent recording gauge stations as a guide. The picture shown below is a graphical example of the mass curve of rainfall. Next is the hyetograph. A hyetograph is a plot of the intensity of rainfall against the time interval. The hyetograph is derived from the mass curve and is usually represented as a bar chart. It is particularly important in the development of design storms to predict extreme floods. The area under a hyetograph represents the total precipitation received in the period. The time interval used depends on the purpose. In urban drainage problems, small durations are used, while in flood flow computations in larger catchments, the intervals are about 6 hours. The picture shown below is an example of a hyetograph of a storm. And last but not the least is the point rainfall. Point rainfall, also known as station rainfall, refers to the rainfall data of a station. Depending upon the need, data can be listed as daily, weekly, monthly, seasonal, or annual values for various periods. Graphically, these data are represented as plots of magnitude versus chronological time in the form of a bar diagram. Such a plot, however, is not convenient for discerning a trend in the rainfall as there will be considerable variations in the rainfall values leading to rapid changes in the plot. The trend is often discerned by the method of moving averages, also known as moving means. Moving average, on the other hand, is a technique for smoothing out the high-frequency fluctuations of a time series and to enable the trend, if any, to be noticed.